Welcome to the Explainer. Okay, today we are looking at something truly revolutionary from the research division of Landry Industries. It's a material known as Hempoxies 54. Over the next few minutes, we're going to explore how this highly programmable, bio-based, circular material is uniquely designed to solve one of the most massive compounding waste problems in modern engineering. Okay, let's dive right into this. Have you ever actually thought about what happens to a giant carbon fiber wind turbine blade, or maybe the ultralight fuselage of a commercial jet when it reaches the end of its operational life? Right now, the answer is kind of grim. Because of the specific science behind how they're manufactured, these massive, incredibly strong structures usually just end up sitting in landfills. They can't simply be melted down or easily recycled. So, why is this happening? Well, it all comes down to a really basic problem in polymer science. On one hand, we have thermosets. These are permanently cross-linked polymers. They're incredibly strong, stiff, and heat-resistant, which is exactly why we use them for extreme things like aerospace and wind turbines. But once they cure, their chemical bonds are locked forever. They are fundamentally unrecyclable. On the other hand, we have thermoplastics. You can melt these down and reform them super easily, but they lack the intense structural resilience and toughness you need for heavy-duty applications. What we urgently need is a totally new generation of adaptable materials that can bridge this gap. So, here is our roadmap for today's explainer. First, the unrecyclable materials problem. Second, meet Hempoxies 54. Third, the magic of vitrimers. Force, multi-scale carbon reinforcement, and finally, the circular materials future. All right, part 1, the unrecyclable materials problem. Look, if we want to transition to truly circular polymer systems, we literally have to abandon permanently cross-linked thermosets. We need networks that can reconfigure themselves, and that brings us directly to the solution detailed in this fascinating research monograph from Landry Industries. Authored by Marie-Soleil Sachat-Landry, this document outlines a chemically adaptive vitrimer composite system. And the best part? At its core, it's based on a completely sustainable, renewable agricultural foundation, epoxidized hemp seed oil, or EHO. Which brings us right to section 2, meet Hempoxies 54. Now, what's really interesting here is the recipe. Let's break down the 5 core ingredients of this highly tuned formulation, designed from the ground up for both sustainability and extreme performance. The base resin is EHO, epoxidized hemp seed oil, making up about 45 to 65% of the mix. Hemp seed oil is fantastic here because of its high polyunsaturated fatty acid content. When it's epoxidized, it gives us 4 to 6 reactive oxirene groups per single molecule. Think of these as multiple chemical hooks that form a massive, robust foundation for the network. We've also got FGE, acting as a reactive diluent, acetic acid serving as our ring opener, zinc acetate acting as the crucial catalyst, and a polyol, like glycerol, to cross-link it all together and control the network density. But getting this right, it's a delicate balancing act. Take the acetic acid, for instance. It operates on a strict Goldilocks principle. You have to keep it perfectly between roughly 4 and 6 weight%. If you use too little, you get an incomplete ring opening, which means your glass transition temperature drops and the material gets way too soft. But if you use too much, you get over-plasticization. The whole thing turns sticky, rubbery, and loses its stiffness. It has to be just right. Moving on to section 3, the magic of vitrimers. To really grasp how this solves our massive waste problem, we need to zoom in and look at how this entirely new classification of material works at the molecular level. A vitrimer is a polymer network that uses associative exchange reactions to keep its cross-link density while changing its physical shape under heat. Let me give you a relatable way to picture this. Think of it like a giant dynamic dance floor. The molecules are all holding hands in a massive interconnected circle. When you apply thermal energy, when you turn up the heat, they can swap partners. The physical shape of the circle rearranges, but they never actually let go or break the chain completely. So the material perfectly preserves its strength and mechanical integrity while still allowing you to move and reshape it. And this brilliantly illustrates the zinc-catalyzed trans-esterification exchange mechanism. Remember that zinc acetate from our recipe? It provides Lewis acidic zinc centers. These are basically the chemical matchmakers that allow those bonds to associate and exchange. And crucially, they do this without depolymerizing, meaning the material doesn't just degrade or fall apart when you heat it up. Oh, and we absolutely have to talk about FGE, or furofuril glycidyl ether. This is the magic molecular bridge in the formulation. FGE is fully biosourced, derived straight from agricultural waste like hemp hurd or corn cobs. It serves an amazing dual purpose. First, it acts as a reactive diluent to drop the processing viscosity. But more importantly, its furon ring creates non-covalent pi-pi bonds with graphitic carbon surfaces. Think of it like molecular Velcro. It literally anchors the bioresin matrix directly to all the physical carbon reinforcements we're putting into it. Let's look at those reinforcements in Section 4, multi-scale carbon reinforcement. What you're seeing here is a hierarchical reinforcement architecture plotted on a logarithmic length scale. Hempoxies 54 doesn't just use one single type of structural fiber like traditional composites do. No, it uses a multi-scale approach spanning 4 distinct length scales. It runs all the way from the macro-polyacrylonitrile-derived carbon fiber on the right, down through the micro and nano phases, ending at molecular cellulose nanocrystals, or CNCs, on the far left. Let's walk through what each of these scales actually does. At the macro level, greater than 1 millimeter, we have the PAN carbon fiber providing the primary load-bearing backbone. Now, to get this graphitic fiber to properly bond with our bioresin, it does require an oxidative and silane surface treatment before composite layup. Next, at the micro level, we have biochar, which is crucial for isotropic stress transfer, meaning it spreads physical forces evenly in all directions. Down at the nano level, graphene and hemp nanosheets act to arrest microscopic cracks before they can grow. And finally, at the very bottom molecular level, cellulose nanocrystals provide extreme crystalline stiffness. A massive advantage of this whole system is the sustainable origin of these reinforcements. Many of these critical phases are directly derived from hemp. For instance, that hemp biochar we just mentioned, it's produced by pyrolyzing hemp herds at 400 to 600 degrees Celsius. That creates a high surface area particle that beautifully distributes stress across the entire composite. We're literally taking agricultural waste and turning it into advanced structural reinforcement. Of course, working with materials down at this tiny scale presents some surprising engineering hurdles. You really have to watch out for agglomeration. Those nanoscale cellulose nanocrystals naturally want to hydrogen bond with each other. If they clump together, they completely lose their reinforcement power. To fix this, the processing protocol demands advanced surface tempo oxidation, or using a high-shear mixer to make absolutely sure those nanocrystals don't clump and stay perfectly dispersed throughout the matrix. Finally, Section 5, the circular materials future. So the crucial point here is how we actually bring this dead material back to life. Because it's a vitromer, it allows for solid-state thermal reprocessing. It is a surprisingly simple 4-step process. 1. You grind the end-of-life cured composite down to particles smaller than 5 millimeters. 2. You load that ground material right into a compression mold. 3. You apply 60 to 180 degrees Celsius of heat and some pressure for 30 to 60 minutes. Because of those zinc catalysts we talked about earlier, the molecular bonds just swap partners and fuse the pieces right back together. And finally, step 4, you just let it cool under pressure. And the result of that straightforward process? It is absolutely astounding. You recover 70 to 90% of the material's original tensile strength after the very first thermal reprocessing cycle. You've taken what would normally be permanent, unrecyclable landfill waste and molded it directly into a brand new, high-strength structural part. But what if you need those pure, pristine, intact carbon fibers back? Well, for true end-of-life recycling, Hempoxies 54 also supports solvolysis. By dropping the composite into a small molecule diol solvent, basically a specialized chemical bath, at elevated temperatures, the matrix actually dissolves in just 1 to 4 hours. That means those expensive, intact carbon fibers can be filtered out and recovered with over 80% of their original strength retained. And you do all of this while completely avoiding the highly destructive and energy-intensive pyrolysis processes we currently use to try and recycle conventional epoxies. Which leaves us with a profound final thought for this explainer. I want you to really imagine this. How will our world change when the massive advanced composites making up our wind turbines, aerospace vehicles, and even modern buildings can be effectively melted down, reprocessed, and repoured indefinitely? Hempoxies 54 brilliantly illustrates that a truly circular infrastructure built entirely on programmable, bio-based materials isn't just science fiction anymore. The chemistry is already here. Thank you so much for joining me on this deep dive, and as always, keep seeking out the structural solutions of tomorrow.